Hi everybody and welcome to week 3 of Math 1. So this week we're going to cover two short topics. For the first set of videos, this set of videos will look a bit at geometry, coordinate geometry in particular, and then we'll move on to limits and continuity. So you still have a set of exercises on trigonometry for this week, but then next week, so next week is a short week thanks to Chuseok, we'll have also a short set of exercises on coordinate geometry. So what we'll cover for this particular set of videos is, well, first of all, what is coordinate geometry? What is it about? How can we represent lines with coordinate geometry? How can we represent circles? And then finally, we'll do a more worked out problem together that puts all of these techniques a bit to the test. So let's first talk about what coordinate geometry is and what we can do with it. So coordinate geometry allows us to study geometry, triangles, lines, etc., not through figures and visual interpretation, but through calculations using coordinates. So you'll see this is quite algebraic, a lot of calculations rather than reasoning on figures. So as an example of what coordinate geometry gives us, let's start with computing the distance between 2 points P and Q. And so let's make a nice figure. I have my X and my Y axis. And then I have a point P here and a point Q here. And we want to know the length of this brown line in between the two. This is coordinate geometry, so let's give these 2 points coordinates, x1 and y1, and x2, y2. And what these coordinates mean is basically this value on the x-axis is x1, this value on the x-axis is x2, and likewise on the y-axis I have that this is y1, and this right here is y2. So and let's call what we want to calculate, let's call that D. So now if I draw a nice little right angle triangle like this is my right angle, then what I know in addition is that the length of this side in the right angle triangle is x2 minus x1, and the length of this side is y2 minus y1, so the difference of the coordinates. And if I put these two together, then Pythagoras' theorem tells me that the length of the hypotenuse squared, d squared, is equal to the length of the sides squared, so x1 minus x, or x2 minus x1 squared, plus y2 minus y1 squared. And now if we take the square root of both sides, then we get that d is x2 minus x1 squared, y2 minus y1 squared, and then the square root of that thing. So sometimes when we want to distinguish what point we're calculating the distance between, we'll denote this as d of P and Q to emphasize the distance between P and Q. The next formula that we're going to look at is the formula for the midpoint in between 2 points A and B. So here we'll again make a nice figure like this, x and y, and we take our point P, or sorry, I called it A, so let's stick with A, and let's call this B. And then on this line in between the two, somewhere in the middle, there's a third point M whose coordinates we want to calculate. And M is the midpoint, it's in the middle. So what does that mean? Well, it means that this side right here is the same, has the same length as this interval. So the distance from A to M is equal to the distance from M to B. So let's put some coordinates on this. Let's say that A has coordinates x1, y1, B has coordinates x2, y2, and M has coordinates xm, ym. So then you can again put these values also on the x-axis, so x1, xm, and x2. And on the y-axis we have y1, ym, and then finally y2. And now let's draw two more right angle triangles. Let's take this right angle triangle and this right angle triangle. And let's call this triangle 1 and this triangle 2. So it's getting quite full, but this is all we need. So what we can decide from this figure is that triangle 1 and triangle 2 are congruent. And what does that mean? Well, it means that one triangle is just a translation or a rotation of the other triangle. And why do we know that they're congruent? Well, they share a side that has the same length, and then they also have an angle here that's the same, and an angle here that's the same. It's quite small, but basically the angles are the same, and they share one side. And so from that we get something very nice, which is that the sides of the triangle are of the same length. And in particular, we know that tells us that this side has the same length as this side, and this side has the same length as this side. So let's put some math on that. Let's have a look at what happens to the x values. So that's what I indicated in red here. We have that this length right here, which is xm minus x1, has to be equal to this length right here, which is x2 minus xm. So we get that xm minus x1 is x2 minus xm. And if you clean that up a bit and bring xm to the left-hand side, you'll get that this tells us that xm is x1 plus x2 divided by 2. And likewise for the y values, you will get that ym is y1 plus y2 divided by 2. For the same reason. So what we get from that is that the coordinates for the midpoint m are the average of the x coordinates, the average of the y coordinates. And this is also a formula that we'll use a couple of times. So now let's move on to something that's a little more abstract, but we'll see a couple of examples of this. And it's this so-called notion of a locus of points. So what is a locus? It's a new word, but locus basically just means a shape or a figure. And what does it have to do with coordinate geometry? Well, the locus is basically, or a locus is a set of points that satisfy a given set of conditions. So the conditions that you're given typically don't give you just one point, but they have some freedom in them, and all of the points that satisfy the given conditions, those form what we call a locus. And there's a couple of examples here already on the slide. Let's go through each one in turn. So a circle is a particular example of a locus, because if you think about it, a circle is a collection of points that are at a fixed distance to a given center. So if this is my center C, and I have a distance, let's say this is distance R, then a circle, like the circle with center C and radius R, is all the points that are at distance R from the center. So this is a circle. Not very nicely drawn, but it's basically all the points that are at the same distance R from the center C. Likewise, an ellipse is a particular locus, and you may wonder, what is the condition? Well, here the condition is that the sum of the distances to two fixed points has to be constant. And this is a useful construction that sometimes you can even see in books, or you can try by yourself. If you take two nails and you take a piece of string like this, and then put your pencil inside the string and sort of move your pencil around, you can trace out a nice ellipse as it's shown here on the figure. So these 2 points are the focal points of the ellipse, and the figure that we trace out, that's the ellipse. And so the distance, the sum of the distance that have to be constant is this distance plus this distance, so d1 plus d2 is constant. That's our condition here. And then last, a parabola is also a particular form of locus, and this may be something that is not very familiar. It's a useful thing to keep in mind. But basically, a parabola is the set of points that are at equal distance from a point and a given line. So what that means, if we make a little figure, is this is my coordinate system. So this is for a parabola. Let's say we take a point here on the y-axis, and we take a given line. Let's take the x-axis. Then what we want basically is we want all the points that are at the same distance from this point as from this line. So this could be, for instance, this point. If you look at that, this distance is about the same as this distance. On the other hand, another point that's on the locus could be this one right here. Let's call it Q, because this distance seems more or less equal to this distance right here. And if you do that for all the points that you can find, you'll see that they trace out a nice parabola shape like this, going through the y-axis like this, and then going off to infinity like that. So it's a little bit hard to see on the figure because you have to draw quite carefully, but at the end what you'll get out is this nice parabola shape. So let's actually talk a bit more about the parabola shape. So here what we want to do is, as an example, let's calculate that we indeed get a parabola, or that we get something that looks like a parabola. So what we want to do here is find the locus of points for which, and now our condition follows, the distance to the x-axis is equal to the distance to the point 0, 1. Okay, let's start by making a small figure. What you'll notice with coordinate geometry is that the figure is usually important because it gives you some idea what to look for, but pretty soon you will end up turning everything into equations, and then from that point it's calculation time. So coordinate geometry is often about calculations. So we have a couple of things that we can put on the figure. So we have the point 0, 1 here. Let's call that C, C0, 1. And we also have the x-axis that's going to play an important role. So let's indicate that as well. And now we want to find the equation for all the points P. Let's call them P like this, for which the distance to C is equal to the distance to the x-axis. So this length equal to that length. So let's give P some coordinates. Let's call it x and y. And then we know that the coordinates of this point right here are x, 0. And what can we now say about our conditions? So on the one hand here we have the distance to the x-axis. So let's put that here. So the distance to the x-axis, that's, if we call this point Q, that is dpq. And that has to be equal to the distance to the point 0, 1. So let's put another color. I haven't used my yellow. So on the other side, we'll put the distance to the point 0, 1. So that's dpc. Okay? That's our condition. So now we can calculate the distance from P to Q. That's the square root of, we have to take the difference of the coordinates. So x minus x squared plus y minus 0 squared. And that has to be equal to the square root of, and now the difference between the coordinates P and C, so x minus 0 squared plus y minus 1 squared. And now let's take the square of this to get rid of the square roots, because it's distances, they will always be positive. And let's clean this up a bit, so we get x minus x squared, that is 0, plus y minus 0 squared, that's y squared, and that's equal to x minus 0 squared, x squared, plus y minus 1 squared. And now if you work this out, you get y squared is equal to x squared plus y squared minus 2y plus 1. The y squared cancels, and if we clean this up a bit, we get that y is equal to 1/2 x squared plus 1. And that is the equation for the locus of points that are at the same distance between the x-axis and C. And this traces out a parabola. This is the equation of a parabola. And if you calculate a couple of points, again, what you'll see is that the point P will trace out a parabola like so, and then going off to infinity. Maybe just as a quick aside, if you have something that is of the form y is equal to something something x squared plus something something x plus something something constant, that will most likely be a parabola. So you sort of have this y and then the x squared, that's the telltale sign of a parabola. Something a little bit different but related, and let me move my head out of the way, is the graph of an equation. So locuses, loci are things that you can calculate. Graphs sort of also fit in that framework because a graph of an equation is basically all the points that satisfy the equation. And on the slide I've shown a couple of particular graphs. I've created those graphs using Wolfram Alpha, which is often a good website if you have something complicated and you want to have a look at how it looks like. You don't need to know any specific programming, you could just type in the equation and see what it looks like. It's still a good idea to be able to graph things by hand because on the exam you cannot use Wolfram Alpha. So let's have a look at each of these in turn and unpack it a little bit. So the first one here, the line has equation y is equal to, or I should put that a bit different, x plus 2y is equal to 3. So let's assume for a moment that we don't have this plot from Wolfram Alpha, and let's try to plot that. Well, what do we know? If we put x is 0 in this equation, then we have 2y is equal to 3. So y is equal to 3 over 2. So we know the point with coordinates x 0 and y to 3 over 2. That's going to be on the line. And likewise, if we put y equal to 0, then we get that x is equal to 3. So that's maybe here. X is equal to 3. And then the line is all the points. Like it's the straight line through those 2 points. Indicate that a little bit more. Okay, and we'll see in the next video that lines always have an equation this way. So the second equation that's listed here is y is equal to x squared. This is a parabola. And then the last graph here is the graph of y is the absolute value of x. And this is an interesting one because you can see you have this corner here. So graphs don't necessarily have to be smooth. They can have corners and things. How did we get this particular shape? Let's again see if we can unpack that a little bit. So y is equal to absolute value of x. That's a bit the same as saying y is equal to x for positive x, or x equal to 0, and y is equal to minus x for negative values of x. And if we try to graph that here on the side, then for positive x values rather, we have y is equal to x, and for negative x values over here we have y is equal to minus x, so we get a line with slope minus 1. Y is minus x. Don't worry if you don't know where these lines come from, we'll see what the slope means and the intercept in just a second.